3, 2, 1.
Ah, Perry the Platypus, you're just in time for my lecture on the stagecoach. Good afternoon, good morning. I hope you're doing well. So today we're going to do BCH codes. This could be error-correcting codes that can correct more than one error. You can correct it 2 errors. So BCH, what does it stand for? This is something you're not going to remember. It stands for Buzz Shol Hiri and Hakem. You're never going to remember that. I don't even remember that. Okay, so what we're going to do is going to use constructed code. Error correcting code that correct 2 errors. Okay, it's going to have length to be 15. It's going to have 7 information bits, so it means it's going to have 8 extra bits. I.e., we can come with 7 bits of information, we can calculate 8 extra bits, we can transfer code word of length 15, and that's what we're going to ship over. And that is what we're going to have to find errors in when errors occur. And how are we going to do this? Well, we're going to use what's going to be our favorite field, the field of 16 elements. And we're going to think about this as you take the polynomials with coefficients modulo 2 and divide out by a favorite irreducible polynomial is x to the 4 plus x plus 1. Alternatively, we can think about this as you start here with the field of 2 elements, and we can join alpha to construct here the field of 16 elements, the Galois field, where alpha satisfies this equation, alpha to the 4 plus alpha plus 1 to 0. So that's the field. Aha. And luckily, we have a table here telling us how to compute inside this field. And I gave you this table the last time I saw you. So now we begin. Before we really begin, I'm going to define m1 of x to be the polynomial x to the 4 plus x plus 1. I'm going to define m3 of x to be the polynomial x to the 4 plus x cubed plus x squared plus x plus 1. So notice these are 2 irreducible polynomials 3 and 4. And the property we're going to need here is that m1 applied to alpha is 0. Okay, alpha is the root, and that's how we defined alpha. But furthermore, the other property we're going to need is that m3 of alpha cubed is 0. That's going to be important. You're going to see this happening. And also the other thing is, you know, that this implies, in fact, that m1 of alpha squared is 0. So finally, polynomial m13 is going to be the product of these 2 polynomials. So note that this polynomial has roots. Well, this is a degree 8 polynomial, but one root is alpha because of this thing. Another root is, of course, alpha squared, this thing. and M13 also have alpha cubed as a root. Because of this thing, so it's 3 consecutive roots. Alpha, alpha squared, and alpha cubed. In fact, we have one more alpha to the 4, but I'm not going to have to using that today. It's going to be later on. So just one more thing to mention here. That the degree of M13 x is 8. Okay, so now you give me 7 information bits. And I'm going to call them A14, A13, A12, A11, don't fall asleep on me, A10, A9, and A8. But you might suspect I don't want to view this as a vector at the moment. I really want to view this thing as a polynomial. F of x is equal to A14 times x to the 14 plus A13 times x to the 13 all the way down to A8 x to the 8. So that's the thing I want to ship over. But now we have to construct the extra bits, 8 extra bits. And you can recognize what I'm doing here. I'm going to take f of x, I'm going to divide it by m13 of x, and I get a remainder. Remainder, and the thing you know about remainder is that the degree of the remainder is less than the degree of this polynomial divided with m13, that's the degree 8. So the remainder has degree at most 7. At most 7. So that means, of course, that the remainder looks like a7 times x to the 7 plus a6 times a to the 6 plus all the way down to the constant term a0. And now my code polynomial c of x, I can define that to be the sum of f of x plus the remainder r of x. Which, of course, now, if you remember I set everything up, this starts as a14 x to the 14 plus to a8 x to the 8 plus a7 x to the 7 down to a0. But more useful for us, well, okay, this is it. But the more useful representation we can think about this is that, remember, we work in modulus 2 on all the coefficients. So when I go and look at this relation, I can move the r of x to the other side. So f of x plus r of x is equal to this thing. So I should write that also. So this is the quotient times m13x. Don't you love it to work modulus 2 plus is equal to minus? So now we have a total of 15 bits. So that's what we can do. We can send bits, A14, A13, all the way down to A0. So this is going to go across the channel, errors occur. Okay, but we are assuming now at most 2 errors. Okay. So when we get it on the other side, we have to put together everything back into polynomial. So we write r of x equal to, and now what can happen? Well, there are 3 cases. Either there is no error, there is 1 error, there's 2 errors. If there is no error, well then this is just c of x we receive. No error. If there's 1 error, it means we have to add in 1 monomial x with I. So this is 1 error in bit I, and I of course ranges between 0 and 14. Or if there are 2 errors, as I realize I don't have enough space to write here, it's c to the x plus x to the I plus x to the j. This is the case of 2 errors in bits I and j, where I and j of course less than 14. Plus one little detail here that we can assume that the errors happened in 2 distinct positions. So now we had to try to, from this information of r of x, we had to reconstruct which case it is, 1 error, 2 errors, or 0 errors, I screwed up what I was saying here, and we had to reconstruct c of x, and with errors we can reconstruct where the errors are. And all that does help at the moment, I want to go back, is, I'm going to go back, how many slides should I go back? Like 1, 2, I should go back to here. I said this thing was important for us. So I want you to now remember that we do have in fact, let's look what c of alpha is equal to. Well, c of alpha, let's bring this down a little bit. I don't know that doing this really well on the camera. Is of course q of alpha times m13 of alpha, but that thing is 0, so the whole thing is 0. So c of alpha is 0. Similarly, c of alpha cubed is q of alpha cubed times m13 of alpha cubed. And yet again, we know that this thing is equal to 0, so the whole thing is equal to 0. So c of alpha and c of alpha cubed evaluate to 0. Well, actually, let me try to sort all my papers here. Okay, so where are we then? Well, we should go back to this thing. And the only thing we can do to help ourselves is to plug in x to be alpha here, and evaluate it, and plug in x to be alpha cubed. So let me do that and see what it will look like. So we have r of alpha in the 3 cases. Well, it can be 0, no error, because I'm really evaluating c of alpha here, and c of alpha is 0. I get alpha to the I, 1 error, and I get alpha to the I plus alpha to the j in 2 error case. And similarly, r of alpha cubed 0 alpha to the 3I and alpha to the 3I plus alpha to 3j. So no error, one error, two errors. So this is the information we have. What can we do? What can we do? Well, truth is, this looks very complicated at the moment. So I want you to look carefully here. This is a dark top hat. And from the magician, no, I'm not taking out a rabbit. I'm going to take out something that can help us here. I'm going to take out a polynomial p of x, and it's going to be equal to r of alpha times x squared plus r of alpha squared times x plus r of alpha cubed plus r of alpha cubed. And I say, this is the polynomial that's going to save us. This is the thing we should look at to determine where the errors are. This seems very mysterious, but like one magic trick, it's supposed to be mysterious in the beginning. So let me rewrite that a little better so you can have it for reference. So p of x is r of alpha times x squared plus r of alpha squared x plus, running over the third time, r of alpha cubed plus r of alpha cubed. Okay. So now I'm going to evaluate this polynomial in the three cases of 0 errors, 1 error, and 2 errors. So let's begin with the easy case, namely no error. No error. Case 1. Well, maybe it should be case 0 because it's 0 errors. Well, then we know, in fact, that if you look no error, r of alpha is 0, r of alpha cubed is 0. They're both equal to 0. So the polynomial, in this case, is just 0. So if no error, we get the 0 polynomial. Great fun. Okay. Now let's go, and hopefully we can distinguish from this from the other cases, and you see we're going to do that. So now let's go to 1 error. One error. Remember then, in the 1 error case, r of alpha is alpha to the I, r of alpha cubed is alpha to the 3I. So that's what we're going to plug in. So let me just write that here so you remember. It's alpha to the I, r of alpha cubed is alpha to the 3I. So then in this case, p of x is equal to alpha to the I times x squared plus, that is square r of alpha, so you have alpha to 2I times x plus r of alpha cubed, that's alpha to the 3I plus r of alpha cubed is alpha to the 3I. But these two are the same, so they cancel. Agree? Remember, like a 2 times 6 and 2 is equal to 0. I think it's about 2. So this is this is alpha to the I times x squared plus alpha to the 2i times x. And if you look at this expression, so let me move up a little bit. You see that both terms contains alpha to the I, both terms contain x, so I can take that out. Alpha to the I times x plus alpha to the I. So this is the second thing about this is the degree in equation. As an equation in x, well, of course, you have one root, x equal to 0. Forget about that. But the non-zero root is alpha to the I. Aha! So we calculate this polynomial, we look for the non-zero root, and then we get alpha to the I. And of course, then when you calculate, it doesn't look like alpha to the 9. If it looks, we have to use to go in and use our table, look it up where it is, and can read up which I is, and find out which bit the error is. Okay? This is just as before, when we did correcting one error. But what we now have to do is we have to look at a case where we have 2 errors. Okay? Life is going to be not much complicated, but let's see what happens. 2 errors. So let's just remind ourselves. R of alpha is alpha to the I plus alpha to the j. R of alpha cubed is alpha to the 3i plus alpha to the 3j. And now we can substitute that in P of x. A magic polynomial came out from the hat, and see what's going to happen. What's going to happen is, of course, we can get a long expression, but bear with me. The magic is going to happen here. Namely, P of x is equal to alpha to the I plus alpha to the j times x squared plus the next term alpha to the I plus alpha to the j squared times x plus, that was a linear term x, and then we're going to have alpha to the I plus alpha to the j cubed, that's r of alpha cubed, and finally we do r of alpha cubed, so that's alpha to the 3i plus alpha to the 3j. Okay, let's simplify this thing. Well, it's not simplify at the moment, it's actually, let's multiply anything up and then see what thing's going to happen. So here we go. This is equal to, well, the first thing I really want to do is I want to expand this thing. And now let's see what's going to happen. We have the binomial theorem expanding a cube. So remember what? Remember that a plus b cubed is a cubed plus 3a squared b plus 3a b squared plus b cubed, since 1, 3, 1 is the rule in Pascal's triangle. You know that. Aha. But when I do this expansion, I get alpha to the 3i, but that's going to cancel with this thing. So the first term in this expansion, that one is that term, and they go away. The last term is alpha to the 3j, and that's when I have over here, and they're going to cancel. So let me try to write this thing out now. Start doing this messy thing. So, I hope you can. Are you still seeing? You're still watching? That's good. Are you still awake over there? I mean, I have no idea when you're watching this. You might watch this at midnight when you're supposed to be sleeping. Okay? Anyway, let's go on. First term is alpha I plus alpha to the j times x squared. The next term is alpha to the I plus alpha to the j squared times x. And now I told you that the first term in this expansion and the last term is cancelled, and then I get the mix up. Remember now, Pascal's triangle, it was 1, 3, 3, 1. Well, none were these terms, 3, 3. But 3 modulus 2 is 1, so I don't have to write out these 3's anymore. So I'm going to get here alpha to the 2i times alpha j plus alpha I times alpha to the 2j. Okay, so this is my P of x. Let's continue simplifying. Let's move the papers around again, right? You can see. Hopefully you can see. But now there's one thing I can do again here. Every term here has an alpha to the I and an alpha to the j. So I can take that out. So I'm mostly working with the constant term in x here. So alpha to the I plus alpha to the j times x squared plus alpha to the I plus alpha to the j squared times x plus alpha to the I times alpha to the j times alpha to the I plus alpha to the j. If you look at it now, you see that every term now here has alpha to the I plus alpha to the j, alpha to the I plus alpha to the j, alpha to the I plus alpha to the j. So we're left with, I can bring that out. I get an x squared term. I get an still have alpha to alpha j, but remember there's a squared here times x plus alpha to I times alpha to the j. And now look at this polynomial, these factors. Well, I have this little mess in the front. There's no x in here. Times. And then the factors as x plus alpha to the I times x plus alpha to the j. Remember now, plus is equal to minus. So what this calculation tells us is that when I set P of x equal to 0, the two roots are alpha to the I and alpha to the j. I had to put an exclamation point because this is amazing. Namely, we take the polynomial P of x. In fact, here is P of x. Yes, Px is this polynomial here that came from the hat, came from nowhere. Oh, here's the thing. Hey, do you see? Wait a moment. I'm writing off the screen. I'm sorry. Here. I forgot what the screen is. Ah. I'd like to write the walls, I write everywhere but I'm supposed to write. So, okay, you get this part, and then setting Px equal to 0, the two roots are alpha to the I and alpha to the j. And I should really say one thing, the two non-zero roots. Okay? So here's the thing, we receive the code word, we use this polynomial back, and then we calculate in each of the three cases here this polynomial, and in the case of, that's not it. I forgot in a 0 case. Can't find my piece of paper there. Ah! I'm losing papers. Yeah, if there's no error, I get the 0 polynomial. And with one error, I get a polynomial with one non-zero root, alpha to the I, and I is the bit with error occurred. And in the case of 2 errors, I get out that the 2 roots of this polynomial is alpha to the I and alpha to the j, which of course means we use a wonderful table of the field of 16 elements, look up which powers of alpha there are, and yes, and that is how the BCH code works. Isn't this amazing? This is the best thing since sliced bread. So the only thing that remains is now to do examples of this. Let's calculate. Let's do an example. So here I'm going to do an example. Actually, let's not do one example. I'm going to work out a bunch of examples so you can see this in action. You can learn to do this, okay? So assume here's example. First example, A14 dot 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 all the way. Here's 15 bits we receive, and I'm going to write them out. 0 0 1 0 1 1 0 1 0 1 and 0 0 1 1 0. Okay, that's bits we receive. What does this mean? That means that our polynomial R of x is equal to, okay, you have to be careful now, this is the 14th bit, so the first non-zero bit is the 12, so it's x to the 12, plus the next one is x to the 10, then we have x to the 9, then we have x to the 7, then we have x to the 5, then we have x squared, and then we have x. So the first step here is to compute R of alpha and R of alpha cubed. Well, let's begin with R of alpha. So of course, I'll be pedantic first time around. R of alpha is of course equal to alpha to the 12 plus alpha to the 10 plus alpha to the 9 plus alpha to the 7. Don't fall asleep now. Alpha to the 5 plus alpha squared plus alpha. In order to calculate this better, so we can see, let me move it up a little bit here. You're still watching. Where did I do? I need more paper. I'm going to say, well, this is equal to, well, I'm now going to start using the table. I'm not going to be able to point at the table this time as I'm talking to you, so I'm just going to put it next to the thing here. So alpha to the 12, that's going to be alpha cubed, alpha squared, alpha, and 1. Okay, alpha to the 10, that is alpha squared, alpha, and 1. Alpha to the 9, that's 1, 0, 1, 0. Alpha to the 7, 1, 0, 1, 1. Alpha to the 5, 0, 1, 1, 0. Alpha squared, just a square, and then we have an alpha. And add. Remember, everything is mod 2. That's the thing that's fun here. This is just 1. This is 0 because it's even number of zeros. Here we have an even number of zeros again. And here we have an odd number of zeros is 1. So this comes out to be alpha cubed plus 1, which is equal to, you look in the table again, and the last entry is alpha to the 14. Okay? So we have R of alpha. Okay, so let me just write it here so we have it. Good. Next, we had to compute R of alpha cubed. Actually, do I compute? Okay, so R of alpha cubed. So remember, there is my R of x. Let's put another piece of paper here so you don't have to see two calculations once. Maybe I have to push it down a little bit. I hope this is visible. You never know. So here we compute R of alpha cubed. So I just had to substitute alpha cubed into here. 12 times 3 is 36. This is alpha to the 30, alpha to the 27, alpha to the 21, alpha to the 15, alpha to the 6 plus alpha cubed. But remember now, in the field of 16 elements, and with my alpha, my primitive element here, alpha to the 15 is 1. So let me make a note. Recall, alpha to the 15 is 1. So that means that exponents are count modulus 15. So this is really alpha to the 6. This is 1. This is alpha to the 12. This is alpha to the 6. This is 1. This is alpha to the 6. This is alpha cubed. So you can see now there's only one alpha to the 12 here. There is 1, 2, 3 alpha to the 6. 3 is equal to 1. So I get alpha to the 6. There's an alpha cubed here. And finally, 1 plus 1 is equal to 0. So this calculation, so let me move this up here. Hope I don't lose anything. I can do alpha cubed, alpha squared, alpha 1, alpha to the 12, 1, 1, 1, 1, alpha to the 6, 1, 1, 0, 0. And alpha cubed, 1, 0, 0, 0. Add, I get 1, I get 0, I get 1, 1. This is alpha cubed plus alpha plus 1. Alpha cubed plus alpha plus 1. Alpha cubed plus alpha plus 1. This comes out to be, now, excuse me for a moment, I'm a little bit suspicious. Did I screw myself up? Get this to alpha to the 7. Yeah, I get this to alpha to the 7. Okay, sometimes. But the problem is that you're not here to correct me when you're doing this. Usually you always check me at the blackboard and do things correct, but you're not. Okay, so it's a little bit lonely sometimes for me here. This is alpha to the 7. So now let's summarize the two pieces of facts we have. The first fact, piece of information we had, R of alpha was alpha to the 14. R of alpha cubed is alpha to the 7 we calculated. These are the two facts we have. Now let's write down P of x, and we have to see what is this polynomial equal to. Well, we get alpha to the 14 times x squared plus alpha to the 28 times x plus alpha to the 42 plus alpha to the 7. Let's work on simplifying this thing at the moment. Remember, alpha to the 42 powers, we count modulus 15, subtract 30 from this. This is alpha to the 12 plus alpha to the 7. If you just look this very quickly, okay, alpha to the 12 is 1, 1, 1, 1. Alpha to the 7 is 1, 0, 1, 1. If I sum that up, I get 0, 1, 0, 0. So this is equal to alpha squared. So P of x is alpha to the 14 x squared plus alpha to the 28 x plus alpha squared. You look at this thing and you realize this is not the zero polynomial, so errors did occur. This does not have x equal to 0 as a root, so hence we know that 2 errors occurred. So what we had to do at this point is set P of x equal to 0 and solve this quadratic equation in x. How do you solve a quadratic equation in x? Well, this is a very famous way to solve quadratic equations. You all know it. Unfortunately, I had to look it up last night, so don't forget this. It's called the quadratic formula. So just to remind you, the quadratic formula, it says that a x squared plus bx plus c equals 0. The root to this equation is given by minus b plus minus the square root of b squared minus 4ac divided by 2a. There's the quadratic formula. You look at this thing, and horror, you observe something. My goodness, this is 2 here. But 2 is equal to 0. That means, in the quadratic formula, you divide them by 0. And there was one thing you've been taught for kindergarten, all for high school, you are not allowed to divide by 0. The quadratic formula is completely useless. You can't use that here. What do we do instead? Well, here's the equation we have to solve. What should we do with it? Well, in your CD players, well, you have to remember one thing. We're looking for a solution in the field of 16 elements. There's only 16 things to check. We could actually start checking, is 1 a root? Is alpha a root? Is alpha square root? Is alpha cubed root? Alpha 4, all the way up to alpha to the 14. And that's actually what happens in your CD players. It's very quick and efficient to check when you have a polynomial, what are the roots? You just go all the powers alpha, and there you go. And it's very good. You can it's nicely implemented into the hardware. There's no problem at all. However, I don't want to check 16 elements to see if they're roots to my equation here. So instead, I'm going to make it a little easier for us to check this and find the roots. Namely, the first thing in solving it is that I want to make the clean. I want to divide through the alpha to the 14, so I have a clean x squared coefficient. Well, dividing by alpha at 14 here is multiplying by alpha. Remember, alpha to the 15 is 1. So I'm going to look at the equation alpha times p of x then I get a clean x squared. I get alpha to the 29. Well, remember 29 mod 15 is 14, so I really have alpha to the 14 here. And then, remember I multiply through with an alpha, so oh, I forget the x here. And then an alpha cubed. So this is the equation I have to solve. And you know that we know that you can factor as alpha to the I times alpha to the j. So look at it. This says that the linear term this is alpha to the 14 should be equal alpha to the I plus alpha to the j. Constant says that alpha cubed is equal to alpha I times alpha to the j, which of course is alpha to the I plus j in the exponent. So this is really says that 3 is congruent to I plus j mod 15. So what I can do is to list all possible I and j's, so they sum to 15. I'm sorry. So they sum to 3 modulus 15. I plus j is equal to 3 modulus 15. So here we go. I can make a nice little table. So the things I have to remember is two things I have to remember. My first relation I have to work in here is equal to 3 mod 15. And the other thing I have to verify now is alpha to the I plus alpha to j should be equal to alpha to the 14. Well, alpha to the 14, same thing as alpha cubed plus 1. So you can make a table, I, j. Well, how many ways can it be? Well, of course it's 3, 0. Then I can increase I to be 4. Means I decrease j to minus 1, that's actually then 14. I can have 5, 13. Remember, 5 plus 13 is 18, which is 3 mod 15. Then I can have 6, 12. They add to 18, which is 3 mod 15. Then I have 7, 11, famous store. And we have 8, 10, and I'm missing one. Oh, I'm missing the one previously. I can 2, 1 also, okay? I'm sorry, 2, 1. So notice in general, these are all the ways to do this, because the order between I and j doesn't matter. So the total number of cases I have to check here is 7. 7 cases to check. So the thing I have to look at is alpha to I plus alpha to the j. But that's easy to do here, because alpha to the I, this is just alpha cubed plus 1. And that's exactly what the thing we were looking for. So we get, we get roots alpha cubed and 1. So the errors are in bits 3 and 0. And we're done. Okay, so that was perhaps a little bit, wasn't too bad to solve that. So let's go back and see around. Here we solve this, here we solve, actually, do you want to look at that one? And I go through here, aha. Here's example 1. So okay, so now you looked at that one. Now here where we started, and the bits was in bit 0, and bit 3 is there. So the corrected thing was sent was 0 0 1 0 1 1 0 1 0 1 0 1 1 1 1. That was the correct code word being sent. Okay. Okay, let's do this one more time, or 3 more times. Okay, let's do another example. The more examples, the happier you'll be. So, here, example 2. Here's the bits we're receiving. One, 0. I tried to write them in groups of 5, so otherwise I will get confused myself. Which you know is quite easy for me to be confused. Okay? That means what? This is what we receive. So R of x is equal to, and here we go again, remember this is 14, x to the 14, x to the 13, x to the 12, and x to the 11, x to 10, 9, 8, 7, x to the 7, 7, 6, 5, x to the 5, plus 1. So the next thing we want to do, compute R of alpha. And I'm not going to write out R of alpha is equal to alpha to the 14 plus alpha to the 13 to alpha to the 12 plus alpha to the 11 plus alpha to the 7 plus alpha to the 5 plus 1. Now I'm just going to directly go for the table. We can speed up. So here we look at the table. Alpha to the 14. Well, good. Sorry about that. Alpha to 14 is 1, 0, 1. Alpha to the 13 is 1, 1, 0, 1. Alpha to the 12, 1, 1, 1, 1. Alpha to 11, 1, 1, 1, 0. Alpha to the 7, 1, 0, 1, 1. Alpha to the 5, 0, 1, 1, 0. And then finally 1 is of course 1. And add all these all up and add. So I add 1, 2, 3, 4, 5. 5 is odd, so it's 1. 1, 2, 3, 4 is even, 0. 1, 2, 3, 4 even, 0. 1, 2, 3, 4, 5 is a 1. So this is alpha cubed plus 1, and alpha cubed plus 1, we look in the table again, is alpha to the 14. So we have here R of alpha, alpha to the 14. Next thing is we have to compute R of alpha cubed. After this, okay, now I'm going to write out what R of alpha cubed is equal to, because if I don't write it out, I'm going to be confused. Oh, cubed. That's 3 over there, it's small tiny 3. I'm sorry, R of alpha cubed is alpha to the 42 plus alpha to the 39 plus alpha to the 36 plus alpha to the 33 plus alpha to the 21, 3 times 7 is 21, plus alpha to the 15 plus 1. Remember now, powers are mod 15. This is alpha to the 12, alpha to the 9, alpha to the 6, alpha cubed, alpha to the 6 plus 1 plus 1. So let's see what we have. We have an alpha to the 12. We have an alpha to the 9. Alpha to the 6 cancel with the alpha to the 6. Then we have an alpha cubed. And 1 plus 1 is 0. So we have alpha to the 12 plus alpha 9 plus alpha cubed. Let me just make this table to add it up. Alpha to the 12 is 1, 1, 1, 1. Alpha to the 9, 1, 0, 1, 0. Alpha cubed is of course alpha cubed. We add it again 1, 1, 0, 1. This is equal to alpha cubed plus alpha squared plus 1, which is equal to alpha to the 13. Aha! So let's quickly summarize. Actually, before I forget, what happened to here? Good. No, not there. Oops, I lost R of alpha. Oh, here. We calculate R of alpha is alpha to the 14. So let me write that on a piece of paper. Yeah. I don't use too much at the moment. R of alpha, you calculate the alpha to the 14. R of alpha cubed, calculate the alpha to the 13. And now we have to take P of x, and we have to solve for P of x. Now we have to calculate P of x, and then to solve for the roots in P of x. Okay. Great fun. So P of x is equal to alpha to the 14x squared, alpha to the 28x plus alpha to the 42 plus alpha to the 13. Well, actually, at this point, I want to get the leading term to be we clean x squared. In order to do that, I should multiply by alpha. So let's just do that. Multiply alpha through by alpha. So alpha P of x. Well, I multiply alpha here. This becomes x squared because alpha to the 15 is 1. Here I get alpha to the 29. The 21 minus 14, 29 minus 15 is 14. So this is alpha to the 14x. This is alpha to the 43. 43 minus 30 is 13. And multiply this one, I get alpha to the 14. So I really want to put that these two constant terms together. And if I look in my table, alpha to 13 plus alpha to 14, this is easy to add because if you look carefully, they're both an alpha cubed term. They have only one alpha squared, nothing done. So the sum of them is alpha used alpha squared. Aha! So my polynomial equation I want to solve is x squared plus alpha to the 14x plus alpha squared. Okay, so in order to solve this, we know, what do we know? This is equal to x plus alpha to the I times x plus alpha to the j. So what we had to get is the alpha I plus alpha j, so big A to the 14. That's the linear term. And then we have the constant term. This is the alpha to I times alpha to the j should be equal alpha squared, or in other words, I plus j is becoming to 2 mod 15. So let's make a table of all the I plus j's to sum to 2 mod 15. So yes, let me keep this thing up here. So here's the table, I, j, and then I have to calculate I, alpha I plus alpha j. Well, it starts with the easiest thing is, of course, 1 plus 1 is 2, but I want the two arrows in two distinct things, so I should really start here and say 2, 0. And now let's go away from this 1, 1 solution, 2, 0. That means I'm going to increase this I by 1, I'm going to decrease by j, so you're going to get 3, 14. No, this is not pi, 3.14. Remember, it's 3 plus 14 is 17, which is 2 mod 15. And now let me just continue to increase I and decrease j. I have 4, 13, I have 5, 12, I have 6, 11, they all add up to 17, this is 2 mod 15, I have 7, 10, and I have 8, 9. So there are the 7 possibilities. And notice if I continue, I would just get 9, 8, which is the same thing as this one, then I get 10, 7, the same thing here. So these are the same, okay? You don't really care for order of the roots, or order of the errors. So now we have to start calculating this thing. What did I want it to be? I wanted alpha I plus alpha j to be alpha to the 14. Looking at my table, alpha to the 14 is alpha cubed plus 1. So I want this to be alpha cubed plus 1. Okay, here, first thing here is of course just alpha squared plus 1. No, that's not what we want. Then I had to take the alpha 14 plus alpha cubed. And if I look in my table, alpha 14 plus alpha cubed, that's going to be 1. Okay, which is not what I want. Then I have alpha 13 plus alpha to 4, and you can actually start doing this with looking at, I get alpha cubed, I get alpha squared, then I get alpha, so I get alpha cubed plus alpha squared plus alpha. No, let me take alpha cubed plus alpha squared plus alpha, but that's not alpha cubed plus 1. Then, now we have alpha to the 12 plus alpha to the 5. Alpha to the 12 is alpha cubed plus alpha squared plus alpha plus 1. And alpha to the 5 is alpha squared plus alpha. I add these two, I get alpha cubed plus 1. Aha! That's exactly what I wanted. So we get the roots. We get I to the 5, j to the 12. Well, order doesn't matter. So roots alpha to the 5 and alpha to the 12. So errors in bits 5 and 12. So let me go, let's go back. Here was this, here was this, here was this. Here errors in bits 5 and 12. That means the errors were bit, that's bit 12. Remember it goes 14, 13, 12, and there's the 5th bit. So the code word that was sent was 1, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1. Ta-da! That's the corrected code word I sent. Isn't this marvelous? But notice the piece of philosophy here is that when errors occur, order of the errors doesn't matter. But yet again, when you solve a quadratic equation, order of the roots doesn't matter. And that's the similarity that makes sometimes part of this click is that roots are like, no, errors are like roots, and that's what we're looking for. Okay, I'm going to continue to bore you here. So I'm going to do another example. I mean, why stop while you're having fun? So let me do example 3 for this thing. Example 3. So here we're going to receive the bits. Okay, here we go again. One, 0, 1, 1, 0. These first 5 bits. Then 1, 0, 1, 1, 1. And then we have 1, 1, 1, 0, 0. Look. Okay, so here let's do another example. I mean, it's like medicine. It's good for you. What can I say? With a spoonful of sugar, the medicine go down. Medicine go down. Medicine go down. Okay, x to the 14 plus x to the 12 plus x to the 11 plus x to the 9 plus x to the 7 plus x to the 6 plus x to the 5 plus x to the 4 plus x cubed plus x squared. A bunch of ones in this being received, so we have pretty many monomials in here. Now I have to compute r of alpha of this thing. Oh my goodness, here we go again. But good for us, what can I say? In fact, well, let me just do this, put this off the screen and just make the table and go. So I'm calculating r of alpha, ugly r, still an ugly r. But you're not taking my class to study my beautiful handwriting, so, or my ugly handwriting, depending on perspective. So, let's not worry about that. Alpha to the 14, 1, 0, 0, 1. So I'm looking at the table doing this. Alpha to the 12, 1, 1, 1, 1. Alpha to the 11, 1, 1, 1, 0. Alpha to the 9, 1, 0, 1, 0. Alpha to the 7, 1, 0, 1, 1. You get bored of this. Alpha to the 6, 1, 1, 0, 0. Alpha to the 5, 0, 1, 1, 0. Now alpha to the 4. Alpha to the 4 is 0, 0, 1, 1. Alpha cubed, 1, 0, 0, 0. And alpha squared, 0, 1, 0, 0. Let me count. Let me count something up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, actually I have 10 rows in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good, I didn't lose anything, at least not yet. Now, we add it up. Are you happy doing things mod 2? I'm always happy doing things mod 2, okay? 1, 2, 3, 4, 5, 6, 7. 1, 1, 2. 1, 2, 3, 4, 5. 1. 1, 2, 3, 4, 5, 6. 0. 1, 2, 3, 4. This is 0. So this is alpha cubed plus alpha squared, which is alpha to the 6th power. Okay, that was nice and convenient. Okay, I can leave it there. Now we have to go for the next thing, out of alpha cubed. Now, there I really want to substitute things in. Be careful. So I have to do, okay, here's r of x. Okay, now we're going to do r of alpha cubed. Hopefully we get lots of cancellation happening, so it'll be a bit less painful to calculate. But first let's write out alpha to the 42, alpha to the 36, alpha to the 33, alpha to the 27, alpha to the 21, alpha to the 18, plus alpha to the 15, plus alpha to the 12, alpha to the 9, and alpha to the 6, which is equal to, okay, this is alpha to the 12 plus alpha to the 6 plus alpha cubed plus alpha to the 12, alpha to the 6, alpha to the 3, alpha to the 15, that's 1, plus alpha 12 plus alpha 9 plus alpha 6. If I now collect terms, have alpha 12, and alpha 12. 3 alpha 12, so 1 alpha 12 left. How many alpha 9s do we have? 1 alpha 9. How many alpha to the 6 we have? 1, 2, 3. So just 1 alpha 6. How many alpha cubes do we have? 1, 2. That's no alpha cubed, and then plus 1. So we only have alpha 12 plus alpha 9 plus alpha 6 plus 1. Okay, so this is equal to alpha 312, looking at the table, it's 1, 1, 1, alpha 9, 1, 0, 1, 0, alpha to the 6, 1, 1, 0, 0, and then 1 is just 1. I add it up, I get 1, 0, 0, 0. This is alpha cubed. So to summarize, at this point, I'll always leave it for just a moment, we have r of alpha is alpha to the 6, and r of alpha cubed is alpha cubed. Okay, so now we have to write down p of x. The polynomial came from the magic hat. There it is. I'm missing the hat in a moment. Oh well. So I'm going to write it down. P of x is equal to alpha to the 6 x squared, alpha to the 12 x plus alpha to the 18 plus alpha cubed. But now look at this. Alpha to the 18 Remember, powers are modulus 15, so alpha to 18 is alpha cubed. So these two add to 0, so I get alpha to the 6 times x squared plus alpha to the 12 times x. I can bring out this factor of alpha to the 6 and there, bring out an x, and then I get x plus alpha to the 6 here. So the non-zero root is alpha to the 6. So error, but there's only one error, okay? There's only one error, that's the first thing. The constant term is 0, it's only one error. Error in bit 6. Aha! Here was the example, we're going to have one error. So, set to go back and find wherever it is. Here long calculation. Here where we started, example 3. Remember now where are the 6 bits? 0, 1, 2, 3, 4, 5, 6. Here is the error. So the correct word is 1, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 0. That was it. Corrected word. Corrected code word. Ha! Wasn't that great? And this is so great. You know, this is like wonderful like sliced bread. So let's do one more example. I know you will love it. I'm sure you will love it. At least you can pretend that you love it. Okay, so let me move things away. And here we go again. And now we do example 4. So the more, the merrier. Example 4, you can receive all the bits now. A14, A0. Here's the bits we receive. I just copy it carefully. 1, 1, 0, 0, 0. 1, 0, 0, 0, 0. 0, 1, 1, 0, 0. Okay? Don't fall asleep on me. Why don't you stop the thing watching in a moment, go pick up something to drink, something small to eat, and then continue. Okay? Or go and take a coughing pause by yourself. Okay, so here for the thing, so r of x is equal to the 14 bit, 13 bits, down to the 9th bit, and then the 3rd bit and the 2nd bit. This is nice, we don't have too many monomials. R of alpha, then we can start adding. Okay, yet again, the wonderful table of the field of 6 elements. The wonderful wizard was 1, 0, 0, 1, that's alpha to the 14, alpha to the 13, 1, 1, 0, 1. Alpha to the 9 is alpha cubed plus alpha. Then we have alpha cubed. Then we have alpha squared. And then we add 0, 0, 1, 0. So we get R of alpha equal to alpha. Good. Next thing. Can you compute? Actually, this. Next we compute R of alpha cubed. This alpha is 42. 2 plus alpha to the 39 plus alpha to the 27 plus alpha to the 9 plus alpha to the 6. So this is alpha. 42 minus 30 is 12. 39 minus 30 is 9. 27 minus 15 is a 12. Goody. Another 12. For alpha to 9 is alpha to 9. Alpha to the 6. So you notice here that the alpha 12s cancel. The alpha, no, this would alpha 12s cancel, and then the alpha 9s cancel. So R of alpha cubed is just alpha to the 6. Wonderful. So we have, I continue on this page. R of alpha is alpha. Let me just write that here so I don't forget. I don't have very much memory. And now we write down polynomial P of x. The magic polynomial that's going to come in and save everything. Okay, so here we go. It's going to be alpha times x squared plus alpha squared times x plus alpha cubed plus r of alpha plus r of alpha cubed with alpha to the 6. Here we are. So we have to compute what this thing is. But alpha to the 6 is alpha squared, alpha cubed plus alpha squared. So this comes out of alpha squared. And now, to make this polynomial better, I want to divide by alpha. So I want to make this term to have no coefficient. So divided by alpha, so P of x divided by alpha, I'm going to have x squared plus alpha times x. And then alpha squared divided by alpha is of course alpha. So here's the equation I want to solve. So remember now, the linear term is the sum of alpha I plus alpha j. This is the linear term. And this says what? That says that alpha I times alpha j should be alpha. But if you look at exponents, it says I plus j should be congruent to 1. Not 15. Okay, so let's put a table of everything when this adds up. So let me put this over here. Now we make a table. I, j, alpha I, alpha j. Okay, I plus j is congruent to 1 mod 15. Add 15 into it. That says I plus j is congruent to 16. That means I can 8 plus 8 would be 16. So I can begin here with 9, 7. I took 8, 8 and increased the first 8 by 1 and I decreased the other 8 by 1. So the sum of them stays the same. And now I can just continue. I get 10, 6. So increasing the i's and decreasing the j's. 11, 5. 12, 4, 13, 3, I get 14, 2, get 15, well 15 is 0, so I write the big zeros, yes, 0, 1. And you notice these are, they have 1, 2, 3, 4, 5, 6, 7. These are all the 7 possibilities. So now we have to calculate alpha I plus alpha j. I will do this mathematic table. It's over here. I'm going to keep it off the screen because otherwise it's not. So if I look at the table and look at alpha 9 plus alpha 7, that becomes 1. Alpha 10 plus alpha to the 6, I get alpha cubed plus alpha plus 1. Okay. Alpha to the 11 plus alpha to the 5, that just becomes alpha cubed. Alpha 12 plus alpha to 14, no, alpha to the 12 plus alpha to the 4. Alpha to the 4 is alpha plus 1. Alpha 12 is alpha cubed plus alpha squared plus alpha plus 1. So it becomes alpha cubed plus alpha squared. Alpha to the 13 plus alpha cubed, that's just alpha squared plus 1. Finally, we have alpha to the 14 plus alpha squared. That, and here we have alpha plus 1. Big disappointment, of course, at this point. Namely, the thing we're looking for, alpha I plus alpha j is equal to alpha, there's no root here. All of them are different from alpha. So, conclusion is, there are no roots. You say, but you promised that we can correct 2 errors. Yeah, I say, that's true. But here's a case where the conclusion is there are 3 or more errors. Namely, all I constructed here was a code that can correct 2 errors. And in life, there could be more than 3 errors. In fact, let's look at this picture and see, could it really be 3 errors? Well, in the codes we looked so far, there's been what we call perfect codes. So let's just look at this code again for the beginning. Namely, change the paper. This was a code with 7 information bits. Well, that says is 2 to the 7 code words. Okay. And then this big picture of how this code looks like. If I take a code word, I can correct 2 errors. That means here's the first ball around of distance 1, and then here's the ball of distance 2 around. Okay? So how big is that ball around this code word? Well, it's 1 plus 15 plus 15 choose 2. Well, so this 1 is for the center itself, no error. 15 is for if there was 1 error. And then when there's 2 errors, you have to pick the position of the 2 errors. There are 15 ways to pick for the first error, 14 ways to pick the second error, and then divide by 2 because there's no order. So if I multiply and see what this is equal to, 1 plus 15, this is 15 times 7. Can someone help me and say what 15 times 7 is? 105 I get this to be. 105. So this is equal to 121. So every code word has 125, including self, words around it that you can correct and get here. So let you see here. That means that in this picture, this code was, remember this is the space of everything of length 15 here, that the size of the ball, each ball here around each code word is 121. Okay, and I have 128 2 to the 7 such balls in here. So let's see what I have. I have 2 to the 7 such balls. Each ball has size 121, and I should compare this with 2 to the 15, which is the bigger size here. Agree? And now we look at this thing, and now I make an estimate. Okay, so I'm estimating 121. Okay, so let's just say that this is about equal to 2 to the 7 times 128, which is 2 to the 7 times 2 to the 7, which is 2 to the 14. So what this tells us, in fact, is that out of all possible space in here, there's empty space here where the 3 or more errors can have occurred. There's things out here, and you see here the proportion. I'm comparing the known world around each code word is size to about 2 to 14 compared to 2 to 15. So more than half of the space here is empty. It's this invisible dark matter out there, things that we cannot correct. So this is the code I presented you that can correct 2 errors. However, most stuff that out there cannot be corrected because more than 2 errors must have occurred when it's sent in transmission. So that's how life is here. But you have to think on the positive side. Now we have a nice code that can correct 2 errors. This is not entirely obvious what these actually things are, but we can now build on it, and from the idea here that solving an equation over these finite fields is actually going to help us find the errors to error correcting codes. There's only one problem left here, and this I have to continue to talk to you about, is not now but in lecture, is that where did this polynomial that solved the problems come from? I mean, I took it from a dark hat. So clearly I haven't given you the whole story how to do this thing. So what I should continue in this class is to give you the background, how this actually happens, i.e. how would I construct and correct more than 2 errors if I want to have a bigger field. So this is really the end of today. So this is all by me. So here's the end credit, professor, me. Assistant, Mike, who knows his last name. Then we want to give acknowledgements. For the help for this. Well, we want to thank B, C, and H who came up with this code. And finally, I think we should also thank Mike who made this whole thing possible, and some person called John, I think, is also now made this possible. So that's it for today. Thank you for watching. Please watch again. Take care and have a good time. Da da dum dum, da da dum, da 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 da, da 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 da, da da dum dum, dum da dum, da 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 dum da dum da dum dum ba dum bum. Bum ba da dum bum bum ba dum bum bum ba da dum dum ba da dum ba da dum ba dum bum da 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 dum dum da dum 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 bum ba da dum ba dum ba dum bum ba dum bum Bum ba da dum bum.